trend or mainstream deep reinforcement learning, basically to use a massive amount of computation and simulation to basically train a reinforcement learning agent that can solve robotic tasks. So this approach is usually working pretty nicely and using some basically sim to real technique. We manage very often to learn very good policy that also work in the real world. So this is basically the mainstream reinforcement learning nowadays, I would say. Oops. I should go back. Okay. And basically, so this pipeline, if I could summarize it in 2 words, consisting before learning in simulation, then apply some domain randomization or some sim to real technique, and then eventually fine-tune the policy in the real world. So as I already mentioned, these deep techniques basically allow you to work with very complex high-dimensional data and solve very complex tasks. So in this respect, they're really amazing. The disadvantage, in my opinion, is that they require powerful simulation and a lot of computation, and I just don't think that this approach is really scalable. Because in the end, what is a simulator? It is a lot of domain knowledge that we need to put to the reinforcement learning agent. And so while I think they really work amazingly for some tasks, I just don't think they are the way to scale up reinforcement learning. And very interestingly, in the early days of robot learning, basically the approach was totally different. So perhaps many of you seen already this video. So this is from the Max Planck Institute. And basically the task considered here, it is to learn table tennis using a robotic manipulator. Okay, I should. And basically the technique that they use, it is to learn before from imitation a policy or a set of policies, and then basically to improve these policies with reinforcement learning. And here in this work, or in some of the work of this classic robot learning era, let's say, there is no use of simulators. Everything it is done just by using imitation learning data, so let's say human demonstrations, and then to improve upon by using reinforcement learning. And this basically proven to be very effective for a limited amount of tasks. So why that? Because basically these classic machine learning tools, they are insufficient to learn complex problems. They are insufficient to learn from high-dimensional data or to deal with complex distribution. However, as already mentioned, they are nice in the way that if some expert data is available, they can use it to simplify the learning process, and they don't require simulation. So I think that one of the main reasons for which these classical robot learning techniques are so sample efficient, so that they can be used on the real robot directly for learning, is that these classical robot learning technique usually use specific models to model the robot behavior. So they have a specific and smart representation of robotic action. And this, I think, is a major contribution already to allow for higher sample efficiency. In contrast, deep reinforcement learning is very adaptive, and they can solve, so with deep reinforcement learning, we can solve a big variety of tasks. And this is thanks to deep neural networks technology, which they can deal with complex and high-dimensional data types. And given enough data, usually we can train these deep reinforcement learning agents to solve very complex problems, but they require a lot of data. So, in short, my hypothesis is that a good action representation is essential for improving sample efficiency. And maybe this is a bit what it lacks nowadays with mainstream deep reinforcement learning, where the policy is just actuating the joins. Okay, so most of deep reinforcement learning methods don't really have a smart way of encoding the policy. So one of my research questions, and the one that I'm going to tackle in today's talk, it is how we can obtain an efficient action representation while still being able to work with complex and high-dimensional data. So my proposed solution, in short, it is to look back of what people have done in classical robot learning, so to take an inspiration from that, and to try to scale this method up by using deep learning techniques. And the key idea that I have is that the typical deep reinforcement learning algorithm, okay, they have a large set of hypotheses or policies, because these policies are very general, and therefore they can encode a rich set of behavior. And this is probably one of the sources that makes these algorithms sample inefficient. While our goal would be to still use neural networks and such, but to somehow restrict the set of policies. So basically to put some inductive biases in these policies, so to restrict the search space. And this should allow us to be more sample efficient. So the pipeline that I'm proposing, it consists of 3 stages. The first stage is that we collect human demonstration, and this is useful to have some insights of the problem, of the task that we need to solve. Then the second stage, it is to use some sort of dimensionality reduction to allow ourselves to extract a meaningful action space. So this action space should not cover the whole set of possible motor skills, for example, but just be able in a compact way to represent the set of useful skills. So in this way, basically to represent the human demonstration. And then we want to use the reinforcement learning by using this particular action space. So what I'm going to present you are basically 4 things. So in first place, I'm giving to you a crash course on the probabilistic movement primitives, which is, in my opinion, one of the smartest way to encode robotic skills or movements, robotic movements. And this is basically a classic techniques that is now very old. So it was developed in 2013. And then we'll see some advantage and disadvantage of this classic technique. And then I will present one of our works, which is a reinforcement learning technique that is used basically in a latent action space that is basically derived with the pipeline that I showed to you. And this work, which we call LAMPO, still uses somehow classical machine learning tools, and therefore it still suffers some of the main problems of these techniques. So it cannot basically scale to complex problems, even though it works very efficiently. So the third things that I'm showing to you, it is basically how can we scale the probabilistic movement primitives to a deep learning framework. And this deep learning framework, I believe that really solves these, let's call them deficiencies, or this limitation of the classic probabilistic movement primitives. So in particular, it will be able to efficiently extract this latent space and to deal with complex distributions and high-dimensional data. And then the first thing I will tell you, it will be how I see basically my future work and what are the conclusions. So let's get started with the crash course on movement primitives. So the big starting point of the movement primitives are robot trajectories. So robot trajectories are basically movement of the robot. So we literally grab the manipulator and we move it from one point to another point, for example, to grab an object. And of course, this motion is a continuous motion. And we discretize it. So at a certain time interval, we record what we call via points. Okay, so we basically sample a subset via points set of robot configuration, and we store it in a data set. And from now on, we denote this robot configuration with the letter Q. Okay? So one thing that we might want to do, since we have a finite amount of via points, one thing we would like to do it is to interpolate these points, so to obtain once again a continuous motion. And if you think about it, that's just basically a regression problem. So in this plot, we have at the x-axis, we have time. So time is the input variable of our regression problem. And the Q is the output variable, the target of our regression. And then we can perform a regression to learn basically the robot movement. And these movement primitives make a linear assumption. So basically, we solve this regression problem utilizing linear regression. So as you can see here, we basically assume that our movement can be described as a linear interpolation of a set of features and a set of parameter omega. So from now on, omega basically are the parameters that describe or that represent our movement. And then the classic Gaussian noise. And you know that this linear regression problem can be solved in closed form, and we can compute basically the set of parameters that minimizes the square error with the human demonstration. So far there is nothing really interesting going on, but I think the major step happens when we put basically a probabilistic model jointly with this linear model. So what we build, it is basically a linear Gaussian model. And in particular, we assume that our parameters come from a Gaussian distribution. And our goal now, it is to estimate the mean and the covariance of such distribution. So that can be done pretty easily. So we just take several trajectories this time. Then we perform a regression or linear regression, more in particular, for each of these trajectories. So we obtain a set of parameters. And then we compute the mean and the covariance of this set of parameters. And this allows us basically to model the mean trajectory and the covariance. Okay, so basically to model the uncertainty of the human demonstration. And by the way, I forgot to mention to you that these features that we are using are usually radial basis function that basically their role it is to be activated at particular time. So this set of parameters have a nice interpretation because then they activate the movement primitive at particular time steps. Okay, so I hope is everything clear so far, otherwise feel free to interrupt me. So why do we care about having a probabilistic model that describes our motion? For several reasons. And the two that are mostly interesting for us are the first two. So the first one is that in this way, we can capture the uncertainty of the demonstrator, and we can use this uncertainty to implement basically a stochastic policy. And this will be useful in reinforcement learning to allow exploration. And in second place, once we have this probabilistic model, we can do a lot of smart things. So basically, we can query this probabilistic model on some condition that we wish. For example, we could sample only movements that passes through a particular via point, or we can learn also the distribution of states of the environment. For example, I can record the position of a bottle of water, and then I can condition this distribution, okay? And I can ask the model, please sample movements, okay? That basically are conditioned on a particular position of this bottle. And we can learn this relation between the two variables, and we can condition this probability. And we can do a number of other things. But probabilistic movement primitives alone also have several limitations. And one of these limitations is that they cannot represent complex data distributions. So, for example, imagine that you want to solve a task, and you have two ways to solve this task. One, it is to perform trajectories on the left of an obstacle, and one, it is to perform basically the motion on the right of this obstacle. As you can imagine, if you're using a Gaussian assumption, then what our model will learn, it is just the mean behavior. And this is exactly what we don't want. So we don't want that our model samples trajectories that goes through the obstacle, but we want actually to learn the bimodality of this distribution. So that's something that for sure it's a big limitation of these probabilistic movement primitives. And also, another limitation, I would say, of this classical robot learning pipeline is that usually this pipeline works in this way. So we learn basically a movement primitives, a probability of movement primitives using human trajectories. And then this gives us a starting point. Sorry, the slide is not rendered very well, but anyway. So this is basically the policy from imitation learning. And then when we use reinforcement learning, we are still inside this large set of policies, because this parameter omega can express a very rich set of behaviors. While what we would like to do, it is to use these human demonstrations to find basically a subset of policies, so a smart representation of this set of movements. And then we want to perform the policy optimization inside this set. And basically, we can do that by, instead of using the parameter vector that describe the movement primitive, we should instead work in a latent space. So this is usually a low-dimensional representation of this vector. And this we can remove basically a lot of dimensions from this vector, because we are not interested in representing any motion possible, but just to focus on a particular and relevant subset of motor skill. So for example, if my task is just to grab the bottle, I don't want to be able to represent also a shaking behavior, because this behavior will not be useful for my task. And this dimensionality reduction is feasible. And we can see that by analyzing basically the movement, the parameters of the movement primitives. So I've done this in my PhD thesis, so this is not really published in any paper, it's just in my thesis. But basically, if we just consider one fixed task, we will have a lot of movements that are very similar with each other. And that means, in first place, that we will have some a redundancy in the joint space. So some joints will have a high correlation. And also we will have some time correlation. And when we have a lot of correlations, it means that there is some redundancy. And if we are able to remove this redundancy, then we are able to compress the information. So this is basically the driving idea how we can find a latent representation of the robotic movements. So and this brings me to the basically first work that I'm going to present today, which is this latent movement of policy optimization, which in short is called LAMPO. So this is a work that I've done during my PhD in Jan Peter's lab in Darmstadt. So basically, we need to address two main challenges. So when we want to reduce the dimensionality of our movement primitives, okay, and we do that with the goal of later using the reinforcement learning in this lower dimensional space, we need first to be able to encode somehow multimodalities, okay? We don't want to have the problem that I mentioned to you before, that basically when we have complex density of data like bimodalities, we don't want to collapse to the mean behavior. And we can solve this by using a mixture model. So this mixture model can help us to capture the multimodality of the data, and so to deal with more complex data sets and more complex tasks. And the second thing is we want to use some dimensionality reduction technique to be able to find this useful latent space. And when I did a bit of research on this, I found this amazing paper. So I really like this paper. It is from Tipping and Bishop, and that's a mixture of probabilistic principal component analyzers. So basically, this paper is a paper about a mixture of Gaussian, and each Gaussian is a probabilistic principal component analyzers. And by using this technique, we can do both. We can first deal with multimodality, and second, we can also perform dimensionality reduction jointly. And the second idea of this paper was basically to create an ad hoc reinforcement learning algorithm that is particularly efficient joint with this mixture of probabilistic PCAs. But I won't focus much on this reinforcement learning algorithm, while I will tell you a bit more about this mixture of PPCA. Okay, so basically the whole algorithm, the whole LAMPO idea, it is first to take a set of demonstrations. So this demonstration, we can learn basically movement primitives. So basically the parameters of these movement primitives denoted with omega, and also some context variables. These context variables are basically the state of the environment. And then with the mixture of probabilistic principal component analyzers, we can learn the joint distribution of the movement and of this context or states. And at the same time, while learning this distribution, we also learn a latent representation. And eventually, once this work is done, we we perform some reinforcement learning policy optimization. So this stage will be a bit similar to REPS, if you are familiar with. And the whole idea is that this reinforcement learning algorithm does not change the entirety of the parameters of the mixture, but instead just focuses on a subset. Okay?
Mm-hmm. Yeah. Can I ask a quick question?
Yes,
Maybe
please.
related to this as well. So I was just wondering if there are any constraints or assumptions on C, like what type of information can come from the environment? Can it be images or videos or audio?
No, this I will come later to that, but basically these are low-dimensional information because basically this mixture of PPCA cannot really deal with high-dimensional information. So in our work would be position of objects or, for example, a desired goal. So in one of the experiments, we had that the robot should pour a quantity of liquid in a bowl, and the context will be this amount of liquid, which was a scalar variable.
Okay, but it's not totally a limitation. It's just a scaling challenge of dealing with like learning a representation over a really large feature space.
Yes, yes, that's
Sure.
I agree with that. Yes.
Okay,
So
thank you.
thanks for the question. And yeah, so basically, so I'm skipping a bit of details and simplifying a bit things, but I think maybe I can present you in a short time what is the idea of probabilistic PCA, if you maybe are not familiar with. So basically, this is just like PCA, but the setup is probabilistic. So we have a latent variable Z, which is basically the low-dimensional representation. And we assume this representation to be Gaussian. And then we assume that our high-dimensional representation, which in this case is the parameter that describes the robot movement, it is just basically a linear transformation of this variable. And then basically by using the bias rule, we can find both the encoder and the decoder. So the posterior is basically an encoder. So we can give this high dimensional information, which is the whole parameters of my robot movement. And the answer to this question will be the low dimensional variable. So this guy is basically doing encoding. And this other guy does the decoding. So the likelihood here, the model likelihood is basically a decoding. And we have this prior. And the nice things about PPCA is that we can train it with expectation maximization. So this is really a natural fit to this more complex scenario of the mixture of probabilistic PCA. Basically, we just need to modify one thing. So we have now two latent variables. One is this continuous Gaussian variable Z, and then we will have a discrete categorical variable. And then we assume that our parameters of the movement primitives are basically are still a linear interpolation, a linear transformation of the variable Z, but we have many possible linear transformations. So this K basically select a particular linear transformation. So before with PPCA, we had a Gaussian linear model. And now we have instead of mixture of linear Gaussian models. But still, in the end, the model hasn't changed so much. So still we have the encoder, the decoder, and the prior. And in the end, what we really need is to learn this decoder. Because in the end, with reinforcement learning, we will have a policy that will generate these latent variables, Z and K, and then we will need to reconstruct the original movement. So this is actually our objective, what we really want to learn. And once we have this decoder, okay, we have basically this an objective, which is to maximize the expected reward. And the expected reward basically can be computed with these three components. Okay, here there is a little typo, but I forgot to clean up this equation. But I think you can grasp the main concept of this. So we have the effect of the policy. So the policy takes as input a particular state and outputs the latent variables. So these are a latent representation of the motion. And then we need basically to decode this latent representation into the high-dimensional representation omega. And then finally, we usually have that the reward signal depends on the motion that I'm performing in the environment. And notice that this maximization procedure just basically modifies the policy and does not touch instead the decoder, which remains fixed. And we do that by using a new reps-like algorithm. So basically, this algorithm achieve what we wanted to achieve. So instead of having this classical pipeline where we take the demonstrations and we use this demonstration only to learn the initial solution, this algorithm actually learns also a compact representation of the demonstrations, and then the policy search just happens in this space. So basically discarding solutions that we think are irrelevant. So now we'll show you a couple of results of this technique. Okay, let's skip the motivation. So basically, we tested this algorithm in simulation first. So we learned and tested in simulation with using RLBench. And we before used some demonstration, like of the order of a couple of hundred demonstrations. And then we improved the policy following the scheme that I presented to you. So this is basically the final policy, which is working, I would say, reasonably. And actually, this drawer, the closed drawer, I don't remember exactly how many dimension had the context variable, but was something like between 10 and 20. Now I don't remember exactly. And then we also tested this on the real robot, so without simulation. So I consider this a richer task where the robot needs to point to a target, and the target position it is captured with an OptiTrack. And then also the other task it is to pour a desired amount of liquid in a bowl. So I collect let's say, I don't know, 100 demonstration. You can check better the detail on the paper. And then the imitation learning policy is not really accurate because maybe of stochasticity or other reason. So basically what we need to do it is to improve this by using reinforcement learning. And with reinforcement learning, we managed to have some improvement. So this reinforcement learning stage is also done in the real world. And you can see that now the policy is more precise. And the same goes basically for the pouring task. Okay, but I think that this algorithm still has some major limitation. Maybe yes, with some let's say we could mitigate a bit some of them. But still, so if we don't know the number of components in our mixture, that can be problematic. And also we have these a bit annoying things of using this radial basis function. So because the backbone instead it is still this movement primitives framework that I presented you before. And if you use a very few radial basis function, you will have a super smooth motion, which sometimes you don't want. And if you want to also be able to represent a jerky motion, then you need many radial basis function. And in the end, this is not really adaptive. So maybe we have some motion that are constant initially, and then they have sudden change. And we would like a smarter way to represent this motion. And also, I think that the Gaussian mixture model are really not good in scaling to high dimensional problems. So I've been able to use them on the MNIST dataset, let's say, but not going further than that. So basically, the main idea it is to, instead of using this classical machine learning tool, it is to use something a bit more modern. So basically a neural network. And we know that neural networks usually are amazing to deal with high dimensional data and complex distribution. But how we can do that? So this is the question that Michael and I and the other collaborator tried to answer. So when I met Michael in the University of Alberta, I basically told Michael, hey, we have this problem. And Michael was more than me a deep learning guy. And so basically together we figure out the algorithm that I'm going to present to you. And I really like this algorithm because I think this is basically the natural evolution of the movement primitive framework. So it basically, even the equation look somehow similar. They resemble the movement primitives, and the movement primitives framework have a lot of nice property. And with these deep probabilistic movement primitives, we are still able to encode all of these nice properties. So this paper just focuses on the dimensionality reduction and the imitation learning phase. So we don't consider here the reinforcement learning. And the first idea for the dimensionality reduction, it is to use variational autoencoders. So variational autoencoders are a very powerful tool that basically works similar somehow to the mixture of PPCA that I showed you before, in that they have again a decoder and encoder architecture. But this is done by using variational inference, and with this we can really encode complex distribution. And as you can see here, we still have this variable z, which is the latent variable that we want to use later with reinforcement learning. Here we have a new variable, which is A, which is the set of via points that encodes a particular trajectory. Okay. The second thing is that these trajectories, so this set of via points A, they should have, and they must have, I would say, even a different length. Maybe in the training phase, we can fix these trajectories to have all the same length in the number of via points. But when we use the model, when we want to query the model, sometimes we want just to use one via point, sometimes we want to use 0 via points, sometimes we want to use 10 via points, or maybe we want to use entirely different variables. And we might want to consider a variable number of state variable 2. Why not? And this is nicely done with this Bayesian aggregation. So the Bayesian aggregation is a technique to take a variable number of inputs and basically find a feature that describes this variable number of input. And we really liked this Bayesian context aggregation because it is a probabilistic framing of the problem which really goes along well with the variational autoencoders that I've presented. So we managed to maintain all our model fully probabilistic. And basically, this model just works by taking basically the production of basically individual feature extraction, but we will see this later. So as I mentioned, so this paper is basically, it takes variational autoencoder and Bayesian aggregation and works with the two of them together. So the Bayesian aggregation in the end basically forms the encoder, and then we use this for encoding in the variational autoencoder. So now I would like to tell you our particular variational autoencoder architecture, which is pretty simple. So for one moment, we will forget about the aggregation problem. So the idea is that we give as input basically a set of VIA points. Okay, so our basically VIA points that represent a trajectory. And then the output of our encoder architecture is basically a distribution of our latent variable, Z. Okay, so our model output the mean and the variance of Z. So again, we have a Gaussian assumption on Z. And then the nice part is that Z is taken as input of a non-linear model. So basically, even though we have a Gaussian latent variable, then this non-linear layer allows us to represent complex distribution. And in particular, this decoder takes this latent variable as the input and also time. So in this way, we just don't reconstruct only the single VIA points, but we can change this variable t, this time variable, to basically reconstruct our movement continuously. So this is basically doing the same things I've showed to you in one of the very first slides, where we say that the movement primitive essentially does an interpolation of points. So this is still one of the things that our architecture does. But more than that, our variational autoencoder is able to capture a complex distribution of trajectories. So this is the motivation for which we are using this architecture. And secondly, I mentioned to you that for a different motivation, these trajectories or even other variables that we want to input to this model, we want the number of this variable to be variable. So we want to have a different number of variables to deal with. And this Bayesian aggregation works basically to use the same autoencoder multiple times and to output different Gaussian distribution of our context. So this is basically representing my belief. If I just consider one variable, then I will have a different belief of my latent variable if I consider another variable. And then basically consider all these distribution jointly. So I take basically the product of the density of Gaussian variables. And this is known in closed form. So this is again Gaussian. And this is basically our aggregation step. And then the output, it is the joint combination of this Gaussian, which is still a Gaussian. And then we plug this aggregation into our model. So this is our final model. This is our probabilistic movement primitives. So the advantage, maybe I repeat once more. So there are two advantages. One is that we can represent complex distribution. We can also deal with high dimensional data. And also, of course, there is a third advantage is that we can use a variable number of inputs. So sometimes we just want to sample a movement without knowing anything, so without conditioning, and then we just use the prior. Or otherwise, sometimes we put some extra information, and so we can condition on this model on as many variables as we want. So in the end, we achieved basically our goal of having this compact representation of robotic movement in one single framework. So we avoid this problem of having mixture of models or so on. So now I want to show you like a few things that we can do with this model. So first, we can do via points conditioning. So you can see that we can basically learn a distribution. Maybe you can see it here. So here we have a wide set of movements, and then we can condition our model just to sample one particular movement that goes through this point. And if I increase the number of via points, then the variance, of course, shrinks. And if I condition my model a lot, then the variance shrinks a lot. And then we can do also other things. So as you can see, we can represent bimodal distribution. And thanks to the probabilistic definition of our model, we can do also blending and other things. So I know I'm a bit over time, but now I'm close to the end of the slides. So basically, here I can show how our model works. So here Michael basically has trained this model to pick up and throw in the trash this object all in one model. So these are basically two very different movements that our model can learn. So I would say that the model is quite successful, even if sometimes it fails. And also I would like to mention that the model, it is trained so both with low dimensional variables and also with images. And maybe an additional things that I can show you is that we can also learn rhythmic movements like this one. So I would say it's a powerful model. So in the end, as a conclusion of this talk, I would say that the takeaway is that the first algorithm that I show to you, in my opinion, somehow tells us that performing reinforcement learning in this latent space makes a lot of sense, okay? Because we discard unnecessary information, we discard unnecessary movement and unrelated skills, and we focus on the important things. And then still a limitation was the use of classical machine learning techniques. And I think that with the Michael work, we have been able to show that we can still actually have all the nice properties of these classical probabilistic movement primitives, but scale it up with deep learning methods. So we are able to deal with images and to work with high dimensional space. And in the end, I would say that we more or less achieved this goal of learning this smaller set of policies. So it is still missing a step, basically, many more, I would say, but my next step would be to use this latent space in reinforcement learning. So I'm still working on it. So basically, the idea would be to have a policy that output basically this latent variable and then to use the decoder to reconstruct the robotic movement. And if you're curious, I give you this additional pointer. So I started already working on this project, and I would say that a natural algorithm to scale this up would to use this dynamic decision frequency continuous option framework, which is another work that we have developed in the University of Alberta. So I finally reached the end of my slides. I hope you had a nice time and we can have a nice discussion. Thank you very much.
Any questions? I've got one that I've been thinking about for a little bit, because you talked a lot about the properties of ProMPs, especially for being able to combine trajectories together. One of the other things I liked about movement primitives from what I remember, is that do they have some properties that help them extrapolate to some things that are outside of the data set that is collected? Or is it more guarantees inside of the, like, being able to interpolate prior data?
Sorry, I was one moment distracted with this thing. Can you repeat the question? Sorry.
Yeah, my question is really about how well these models can generalize. Like, do they extrapolate pro-MPs? Like, do they extrapolate well compared to how well that they interpolate?
No, I don't think yet they extrapolate. So this is another line of work that I would do. And I think for that, one way would be to train this movement primitives framework, like a Michael work, on multiple tasks, so on many different tasks, and then to try to somehow generalize also across tasks and learn interesting things about tasks. But when we consider one task at the time, sort of we are a bit overfitting, I would say, on the problem. So yes, we can interpolate between motions, but I don't think we can do much more than that, honestly.
Mm-hmm. Okay. Thank you.
Thanks.
Mm-hmm. Okay.
Maybe one other sort of like larger question. I wonder if you followed the whole sort of diffusion policy style of approach that seems to be becoming popular recently, that also seems like it can kind of handle the multimodality of demonstrations, and what you think about that and how it compares to your approach.
Yeah, so I agree with you. So I think that the diffusion models actually probably do this job better. And I'm really curious in going to this direction, and I would like to see if you are still able to have a model that still is able to encode all the properties of ProMPs, so to have all these nice operation between distributions that you can do with ProMPs. And actually, this is also a question that I wanted to do to you, because I've seen that someone in your lab, Siddhartha, have worked with diffusion policies, and in particular with latent diffusion policies, and I think this is quite related to my work. And I don't know if he is here or not. I would like to hear his opinion too.
He might be in class right now. I'm not entirely sure.
Okay.
Is he on?
I think they look very promising, but I should still wrap my head around on how exactly. Yes, for what I've looked this work, actually, it's very interesting, and some combination actually of the two could also be even a bit nicer, because I've seen that if I understood it correctly, you still needed to have this fixed length of the trajectory. So this is also a question that maybe with Bayesian aggregation can be solved. I don't know. There are a lot of exciting things to do, I think, with the diffusion models.
Interesting, yeah. Cool.
All right.
All right, I guess let's thanks Samuele again for joining us and making time. Thanks so much.
Thanks.
Thanks so much.
Thanks to you. So I hope that maybe we can remain in contact, because I've seen that we have related work, and you know, yeah.
Yeah, would be happy to. I'll catch up, and I'll maybe we can set up a meeting or a chat with Siddharth about some of the many diffusion things we've been looking at lately.
Yes, I agree.
All right. Thanks. Take care, everybody.
Okay, thanks, everybody. Bye.